For our Math Expo project, we had the Northeast Airlines problem. This problem provides us with the diagram of an airline flight map shown here. This map must be made into a matrix. The cities are placed in order on both of the axes in a square matrix. The size of the matrix is equal to the number of cities. Now, if a city has a direct connection with another city, a 1 is placed in the two spots where they intersect. Otherwise, put a 0. For example, take Boston and Washington. They have a direct connection. So a 1 is placed in these two spots. Now on the other hand, take Boston and Chicago. They have no direct connection, so a 0 is placed in these two spots. Once you do this with the entire matrix, you get this matrix that represents the diagram. From this point on, this matrix is going to be referred to as R. Also to note is matrix notation, RMN, M being the x-axis and N being the y-axis. So this cell has the coordinates 3, 2. Next, the problem asks us to square this matrix, but before we do that, we have to go over a matrix multiplication.
To explain, we are going to use these first two matrices. For the purpose of this problem, we only need to look at square matrices of the same size, so the other dimension rules are unnecessary. First, you need to take the first row of A and the first column of B. You take A1, 1, and multiply it by B1, 1. And then multiply A2, 1 by B1, 2. Then multiply A3, 1 by B1, 3. The sum of these three numbers is what goes into C11. So you do the same process except now with the second column of B. When you finish with the last column, you start over with the second row of A. So R squared, or R times R, is the matrix on the right. You may be wondering what the significance of this is. It's actually pretty simple, but pretty interesting too. You remember how R was the number of step, or one direct flights between cities? Well, R squared is the number of two steps, or one layover path between the two given cities. For example, take New York and Washington. There are two one-layer flights between the two, Washington to Boston to New York, and Washington to Chicago to New York. Just for clarification, going from Washington to New York is the same as going from New York to Washington for our purposes. This occurs in the matrices because both cities have a connection to both Chicago and Boston, so those numbers are the ones multiplied. The only ones connected to those are the ones with links.
The problem then asks us to find r cubed. You find this by multiplying r squared by r. As you can see, the matrix on the right is r cubed. R cubed shows the number of 3-step or 2 layover paths between two cities. The reason r cubed works is because r squared shows the number of 2-step paths and r shows the number of 1-step connections. This means that if a third city is connected to both the cities, then there is a 3-step connection between the two cities. As either number increases, so does the number of paths. This is r squared plus r. What this matrix shows is the number of 1 or 2-step flights between any given cities, or 0 and 1 layover trips. This is r cubed plus r squared plus r. This shows the number of 1, 2, and 3-step paths between any given cities, or 0, 1, or 2 layovers.
This is a really useful tool for airline companies to create routes. They can know exactly how many connections there are between cities, even if the number of flights gets very large and complicated. The main drawback to this method is that it only gives you the number of connections, not what the connections actually are. The extension to this problem was to find a real-world example and do the same things, like finding the matrix, squaring it. We found a map of Cape Air in the Caribbean. To do this and solve the problem, we created a program that you can input a flight map into, and it provides you with all the matrices. These are some screen caps of the program. First, you input the number of cities, then their names, then the connections between the cities. This then provides you with the matrices of r, r squared, and r cubed. These are the results.
Just a little help, we also made the program accessible to anyone. I will put a QR code up on screen right now of the program, and we will put a link in the description for you to click on it if you're not using a computer. If you have an iPhone, you can scan the QR code and be able to access the program from your phone right now.